Alright, this is my buoyancy, pressure, and assorted other stuff physics test, direct from Stowe, Vermont. So, for our first problem, we're going to be looking at a U.S. Nimitz-class aircraft carrier, also referred to as a supercarrier. It's the largest aircraft carrier the U.S. Navy has. And what we're going to be looking at is how much volume of the aircraft carrier is actually underwater. So quick internet research will tell us that the aircraft carrier, when in the ocean, displaces 106,300 tons. Now that's the weight of the water displaced by the aircraft carrier, which also then tells us the weight of the carrier itself. So a quick conversion will tell us that that is equal to 96,307,800 kilograms. And so that's the mass of the boat that's underwater. So now with this weight, with this mass, we can also then calculate the downforce on the boat, which is going to be that number, 96,307,800 times 9.8, which gives us 9,416,440 newtons. Now, that's also going to be equal to that's got to be equal to the buoyant force on the boat, because as you can see, the boat floats. So, F buoyant equals 943,816,440 newtons, 440 newtons, which is also equal to rho v g. Now we want to solve for v. So v is going to equal 943,816,440 divided by rho, the density of the water, which is 1,000, times g, 9.8. And that equals 96,307 meters cubed. That is the volume of the aircraft carrier that is under the surface, that is below the surface of the water. So for our second problem, we're going to take a standard garden hose. Now, standard garden hose has a diameter of 3/4 of an inch. And we're going to assume that the velocity of the water as it exits the hose is 2 meters per second. So what we want to find out is if we decrease the velocity, decrease the area, the height of the diameter of the hose, the water will come out at a faster and faster velocity, as shown by the equation A1 V1 equals A2 V2. So, if A1 V1 is one thing, and the A2 decreases, then V2 also must increase. We're going to find out what we have to make A2 be if we want V2 to be the speed of sound, 340.3 meters per second. So hopefully by the end we will have a hose, granted a hose that is strong enough that it won't just break under the pressure, a hose that will shoot water at the speed of sound. So let's first figure out what we know. So let's get our A1 going. So we know that they have 3/4 inch diameter, which translates to which translates to 0.019 meters, which means the radius is equal to 0.0095 meters. So that means that A1 is going to equal pi times the radius, 0.0095 squared. And then we know that, which is equal to 9.025 times 10 to the negative fifth pi. When we get our V1 equals 2 meters per second. Then we've got A2 is our unknown. V2 equals 340.3 meters per second. And so now we just set up an equation just like this one. And so we can see with this one, we can go right ahead and divide each side by V2, and that will give us what we want, A2. So let's pick purple. So A2, let's use purple. A2 is going to equal A1V1 over V2. And we know all of these values. So A2 is going to equal 9.02 times 10 to the negative fifth pi times 2 all over 340.3. That gives us A2 is equal to 5.3 times 10 to the negative seventh pi. And then, so that means that A2, that equals 7.3 times 10 to the negative seventh meters, or 0.73 millimeters. Sorry, the radius equals 0.73 millimeters if the speed of the water is to be the speed of sound. So for the final problem, we're going to use the properties of metals to expand when they are heated, to lengthen when they are heated. To demonstrate this, we're going to see how many degrees Celsius we would need to raise the temperature to make a bridge across the San Francisco Bay using only a 10-meter long piece of iron. The idea is that if we can assume that the iron does not melt when it is heated, it will simply lengthen how hot it would need to get for this piece of iron to span the width of the Golden Gate Bridge. So the equation we're going to be using for this is the change of length, which is alpha equals delta L over L delta T. This is the coefficient of linear expansion equals the change in length over the original length and the change in temperature. So we can rework this to suit our needs, which means that we want to find a delta T. Delta T is going to equal delta T is going to equal delta L over alpha L. So we know most of these things. We know that alpha for iron is 12 times 10 to the negative 6th, and we know that delta L we want to be the length of the Golden Gate Bridge, which is 2,737 meters. And we know the current length, which is 10 meters. So we plug in what we know, we get delta T equals 2737 over alpha 12 times 10 to the negative 6th times 10, and the delta T equals 22,725,000 degrees Celsius. So if we raise the air temperature by 22,725,000 degrees Celsius, this 10-meter long piece of iron will be 2,737 meters long.